Okay, let's give this a try. Hello folks, this is Mark Wood speaking. Some of you guys know me, some of you are followers. I wanted to talk a little bit today about electric control line model airplanes, and they're quite a bit of fun. They work really well today. Batteries are getting better and motors are getting better, and so the performance of the airplanes are getting better. There's a number of advantages and disadvantages. Some people like them, some people don't. This session is about a general overview, basic operations, and how these things work, and a little bit of my perspective, having used a few different systems, and having received a bunch of questions about what you have to have, and recommendations and so forth. And this is a overview of one of the simplest system architectures that you can use to build an airplane and fly it. So, quick overview of what's necessary. You have to have an energy source. In this case, our energy source is a battery. And today, these lithium polymer batteries provide the best source of energy for electric motors. Lithium has a lot of energy that it can store, and these lithium polymer batteries are light, and their energy storage per pound is sufficient to be quite good for our model airplane arena. Fuel still tends to be the winner in the BTUs per pound or energy per pound storage, but batteries are coming along, electric systems are coming along, and they have some advantages of their own. Simple operation, low noise signature, amongst probably the most desirable characteristics of electric systems, and weight being probably the least desirable. Electric systems tend to not be the best in terms of weight per power. So here's an overview. You need a battery, you need an electronic speed controller, obviously you need a motor, and for our control line airplanes, we need a timer. And the timer on our control line airplanes replaces the receiver that we have in RC aircrafts. And its basic function, I've diagrammed here, its basic function is it operates as a throttle control. In the RC world, the throttle control output from the receiver would drive a servo. And our ESC, our speed controller, acts like a throttle servo. And so it receives, in essence, from the receiver or our timer controller, a throttle command that looks like a servo. And so the ESC then converts that throttle command into a driving wave function for the brushless motor. The interesting thing about a brushless motor is that it really is, we call it a DC brushless motor or brushless DC motor, that kind of thing. But basically, this motor right here, this motor is a three-phase AC motor, and so it works. And if we drove it with AC power, it would work just like any other motor. The magic here is that our ESC uses a DC power scheme such that it drives the phases in the motor in a way that the motor works. And this is all the result of our modern microcontroller RISC controller systems that we're able to build today with these very, very small computers, very simple set computers. We call them microcontrollers. They receive one program and they run it. So the way this system works is that in order to have a DC voltage drive our motor, our AC motor, is we have three SCR, silicon controlled rectifiers, or MOSFETs that are configured in a particular way. But basically what happens is this device, and this is inside of our speed control. Here's our speed controller. If you were to take this apart, you would see that there's three fairly large pieces of semiconductor parts inside of it. And then there's the computer, basically, that runs. We call it the microcontroller. And these devices can do two things. They can either supply voltage or they can supply a ground. And so if we take the DC motor or the AC motor in its basic configuration, I've drawn it here. And so what happens is the windings in this motor are all tied together, and they're tied together in one place, and then on the other side they go out to the line voltages. And so by being able to turn this device on and off, on meaning that it will supply voltage, and off meaning that it will supply ground, if I have two of them, I can turn one on and turn one off. And when I do that, it causes current to pass through this circuit like this. The microcontroller tells which one to turn on and which one to turn off. And so when I have current passing through my coils, the windings in my motor, you can see the windings inside. When I have current passing through the windings, it creates a magnet. And that magnet would have a north and a south pole. I just drew these, and that polar alignment would be dependent on what the direction of the phases are, the coils are. It's really kind of irrelevant. But when the current passes through these two coils, it creates a south pole and a north pole. And the magnets that are in the rotor would tend to align themselves so that the magnet's south pole and its north pole would align opposite to the poles that are being driven by the coils. And so we could think of our motor's rotor wanting to line up like this whenever I turn that first phase on. So what can happen is my microcontroller can take this SCR, turn it on, and then turn the B one on. I've labeled them A, B, and C. It can turn the B on or off, which means it switches to ground, and it aligns my magnet like this. Then just shortly after that, I turn B off and turn C on in the ground mode, and that switches the south pole, makes my current go through a different path through my motor, and now my south pole switches a little bit, and so my motor wants to turn ever so slightly. And if I continue this sequence, now next what I do is I turn the B SCR on and continue the C on the ground side. That will switch my north pole and cause my rotor to turn even further. And if I do this in a sequence and continue to do it in a sequence, and I drew this right here, if I have A and B, and then A and C, and then B and C, and B and A, that causes my poles in my field to switch in a circle, and I can do this continuously. And that's how I drive my motor. I just simply start driving these controls, these SCRs, in an appropriate sequence, and that will drive my magnetic field of the coils in a circuit. And my rotor with the magnets will follow suit. If I'm really clever, I can do this in a manner that causes some of my fields to push and some of them to pull, and I can get a tremendous amount of torque out of my device. It's quite the revelation in terms of electric motor technology. So the next question is, how do I make this thing work? And so if we run this at a specific frequency, the motor will eventually run at a set speed. And while that's very nice and usable, it doesn't do us much good in terms of modelers. In the RC world, we want to drive, or in the car world, we want to drive, we want to accelerate, and we want to slow down and speed up. And so we need a method to drive these in a specific manner. Obviously, if I slow my rate of change, my progression through these switches, then my motor will slow down. And if I speed this up, my motor speed will increase. I could do it at a set frequency, and inertia would help me change my speed if I change my voltage. We're not going to talk too much about how that interaction is, because it's not really that important to what we have to say. It's just we need to have a fundamental understanding of how the speed controller, the ESC, and the motor interact. And then we need to know how the throttle signal interacts to cause the motor controller, the ESC, to output the appropriate signal to the motor. So what we do is we use a method called pulse width modulation. And what pulse width modulation is we turn a signal on and off. And we do it at a specific rate. In the case of the electronic speed controller, it's expecting a signal, a pulse, about every 20 milliseconds. Now, convention is that our throttle signal is going to be on for about 1 millisecond to 2 milliseconds. And by definition, what we've decided is that somewhere around 1 millisecond on time is going to be 0 degrees or off, and somewhere around 2 milliseconds we're going to use or say that our signal is 100% or 180 degrees, depending on how we decide that particular timing is going to be interpreted. In terms of a servo, we would say at 1 millisecond 0 degrees, and at 2 milliseconds 180 degrees, and that would be the rotation of the servo. So the servo would be at 0 at 1 millisecond, and whenever we increase the timing of our signal to 2 milliseconds, the servo would swoo to 180 degrees. In terms of our throttle, it would be throttle off and throttle maximum. 100% maximum throttle would be at 2 milliseconds. I'm going to show you that in a second. I've connected my speed controller. It's connected to the battery. It has inside of the speed controller, there's a battery eliminator circuit, and so it supplies power to my timer. This is my timer. This particular timer is a Hubin FM-0c timer. This is a wonderful little timer, and it has a very simple interface for the user. The interface, I had a screwdriver here just a second ago, right here. The interface has 2 potentiometers, one for power and one for duration, time. If we were flying RC, we would use our throttle stick to start and stop our flight. In the case of our radio control, our control line model airplane, we have a timer. Once this timer starts and the motor starts running and the airplane is flying, this timer counts down for a amount of time that's programmable by this potentiometer. As I recall, the potentiometer is about 1.5 minutes to 5 or 6 minutes total duration. Generally much more than what I tend to like to fly, and sometimes it's a little bit not short enough whenever we're doing test flying. So you can see I've started my oscilloscope right here, and you can see that this yellow signal is the output. I've got my oscilloscope connected to the signal wire on my timer. That's the output of my timer, and you can see that that duration is about 1 millisecond. Because the timer is in off mode, turning my potentiometer has no impact on the throttle because there's no output from this device. So the way this works in flight or to fly is there is a start button right here, and when I push this start button, it tells the timer to begin its program. Right now it's running in a wait state. It's just waiting to be told to start its program. Once it's started, once I push this button, it starts its program, and its program says check the motor to see if it's running, then count down for 30 seconds to allow the pilot to get out to his handle in order to start his flight. And then after 30 seconds countdown, start the motor and go fly. And then at that time, it starts another timer, which is the one that we set with using this pot right here. And that timer says, keep the motor running at your set speed until that timer runs out. So our set speed comes from this power configuration right here. So let me do that. I'm going to start this. And so when I start this, watch this signal right here, and you will see that the signal will ramp up and ramp back down again, and you'll also hear the motor's right here. You'll hear the motor start up and start running. I don't think I can focus on both, but you see this, see how that happens. I'll watch this motor after a bit. Okay, so now we're waiting for the timer to count down as 30 seconds to start the motor for flight. And once it does, it's going to ramp up, and then we can make some minor adjustments on this timer. Eventually what happens is the timer gets into a place where the power, see here it comes, here's my signal, and so it's running. If I take my potentiometer, I can turn it, and you can watch how the signal changes up and the motor slows down. And in here, channel 2, I'm not connected to channel 2 properly, but you can see that whenever I adjust my speed, that signal increases, and then it decreases in its on time. And let me check to make sure how I'm connected here. I'm connected, yes, connected to, and let's jump the signal up. Here we go. And you see right here, this signal is the output from my speed controller to my motor. And this is one of the phases. You can see that the phase is being switched on and switched off. And as I change the speed, my speed doesn't change anymore because my motor has timed out. We've got to reset this system, which I'll do right now. And then we'll be able to see that the frequency changes. DSC is booted. I'll start my time. Have a little coffee while we're waiting. Now ESCs have different modes that they run in, and there's a governor mode generally and a throttle mode. That was my neighbor. That's the PT-19. So you can see now that, let me see if I can get a little better time base for this guy. I've got my trigger going on channel 1. So if I adjust my speed, you can see that the frequency of my speed controller changes as I change my throttle. You can see that inside of this signal there's a bunch of other little bits and artifacts, and those are voltage spikes that the control uses in its sequencing or its governing mode for see if we can do this. Nope, it's saturated, and this thing's about ready to go, so I'm going to shut this down. Okay, so you can see that this is actually a fairly simple device. It's interesting, and you don't need to have things like an oscilloscope. The oscilloscope is interesting because we can look at the waveforms, but for the average everyday user, really all you need to know is that this acts like a throttle, and this makes it the system capable of running this motor. And then the hardest part of this whole thing for a control line flyer is being able to program your speed controller. This speed controller is a very budget-oriented speed controller. It's a ZTW beatless 20 amp speed controller. It'll run fairly decent sized motors depending. This is a programming card, and there's a number of features on here that are interesting to us as our control line operations people. So you can see it has a feature here. It says a battery. I want to program for a lithium polymer battery, LiPo. It says heli mode. Heli mode is just another word for governor, and what the governor does is it tries to maintain a set RPM range, and it does that in a number of different ways, and depending on how sophisticated the ESC is, the governor can work quite well. Most of these low-end governors, I believe, are generally just an open loop style of governing system, which it tries to maintain a specific frequency voltage relationship, about one order of magnitude removed from just a simple throttle control. So this jumper here, this is how this works. There's some jumpers, and you move the jumper from pairs of pins around to program the speed controller. Generally what happens is the governor 1 first range, governor 2 second range, there's a lot of different terminology for them, but basically what that means is how fast the governor is going to ramp up to its set speed. The set speed really comes from the throttle position in our controller. When we're using a radio control, what happens is you have a switch, and you switch that switch, and it puts the it's called an idle up switch. When you switch that switch, it sets the throttle to a fixed value. Sometimes that throttle has a little bit of gain movement in it, so that whenever you raise the collective, it adds some throttle. That's useful in our control line, but not for your basic sport model. So this governing mode just tells you the range, or governing 1, governing 2 just tells you how quickly the acceleration to set speed will be. And then this start feature is how fast the throttle will come on whenever you start the motor. Somewhere between soft and very soft is acceptable, or even a rapid acceleration, which is a start acceleration. That's okay. The brake function is whenever the throttle is backed off, it causes a little back current to stop the propeller to make a very good, whenever the airplane is coming down, a very good resistance to decay. Here's a feature that's called timing. If you don't understand this, you can set it on auto and it works just fine. Or you can set on a multi-pole motor like this one, you can set it in the high range. Basically what that is that the current and the voltage relationship between this motor when it's spinning are not perfectly in phase. And so the better that you can drive that current to the response of the motor, the more efficient the motor will be in using power. And for sport flying, you can take this and select this to auto, and it's going to work just fine. There's a rotation, normal and reverse. And this is something that you don't necessarily have to have programmed in your control. If your motor is running backwards, you can simply take any two wires and switch them, and the motor will run in the direction you want. And then there's this cutoff voltage. How low per cell is the voltage going to be when the speed controller decides that it's no longer going to run the motor? That's important, because that's how you keep the speed controller from destroying your batteries. And then finally, there's this option on this one that says cut off power. You can either slowly reduce the power or you can stop it. And I've used both. I currently fly with my cutoff power in the stop position, because what happens is whenever you have the reduced power, it slowly reduces the power, and then the airplane settles and it won't fly at a low power, but it won't quite shut off enough to land, and you end up landing in a place you don't want to land. So I just put it on stop. So this is very, very easy to program. If we did not have this device, and this is very expensive, it's like $7. And this programs all of my various ZTW beatless controllers, and I have several of them, and I've worked with them, and they work just fine for the sport models. They take a little tuning for the competition style model, but that's a different subject, and it requires a different timer. This is a very basic timer. So to program the speed controller is very simple. You can disconnect either at the speed controller or right here. What I have here is just a means. This is a jumper. I've gone from my speed controller to this prototype board to my timer in order for me to be able to pull signals off in order to run my oscilloscope. And so to program my speed controller, I just simply disconnect the speed controller or my timer, and I plug it back in, and then I plug my speed controller back in, and then when the speed controller, the motor beeps like that, it's programmed. Super simple, very easy. Nothing to panic about. Now my system is ready to run. I plug it back in. It's going to go beep, beep, beep to confirm. You can't hear the beeping because of the motor being mounted on this, but you could hear it on your airplane. So you can see that my signal is back alive. I can turn this on. It runs. And it's going to start. When I set my power, I can go outside. Inside here with my AC lights, there's too much flicker, and my optical tachometer does not work. So we go outside where the sun is working, and then we can see the propeller blade and set the power. So here we go. So I just dial this up, dial it down, set my power where I want it, you know, 11,000 RPM or 10,000 RPM or 13,000 RPM, and the airplane's ready to go. Hopefully this helps you out. Gives you a little understanding how the system works, what you need, and how to program and adjust it. This is what my words are. If you've been contemplating going with an electric model, do it. If the technology is giving you consternation and you're afraid of the technology, don't be. It's a lot simpler than it seems. The very, very, very simple systems like this FM-0c and the beatless speed controller work just fine. There's no need to spend $100 on a speed controller, especially whenever you're starting out. This speed controller here cost, I think I paid $15 for this speed controller. So between the speed controller and my programmer, I'm into this for about less than $25. The electric motor that is on my shoestring here, that electric motor was $29. So I'm under $50 for that part of my power system. This FM-0c is about $20. And this battery won't fly the shoestring, but the 2200 milliamp hour batteries I've been using are about $15 a piece. So for under $100, you have a power plant on your airplane that works quite well. There's videos of my shoestring flying, and you can see that even with this low budget power system, the airplane works very, very well. I fly electric primarily because I fly in my neighborhood and I have neighbors around, and I fly at 6:30 in the morning, and if I was flying gas, they would not be happy with me. If I was flying gas, my opportunities for flying would be once every week or two, and I would not be able to fly very much. With electric, I can fly virtually every day. So anyway, I hope this helps, and I hope you guys enjoy it. Thank you for watching.